Hi ladies and gentlemen, in this video we are going to start section 2.5 independence. In this part we are going to define two independent events. We will show that if A and B are independent, then A prime and B are independent. A and B prime are independent, and A prime and B prime are independent as well. And we will determine the probability of A and B both occurring when A and B are independent events, and we will define the independency of more than two events, and we will clarify the difference between independent events and mutually exclusive events. Here is your homework. Please look at examples 2.31 to 2.35 in section 2.5, and also exercises 66, 67, 68, 70, 71, 72, and 105. You remember that in section 2.4 we talked about conditional probability. For any two events A and B with probability A greater than 0, the conditional probability of A given that B has occurred previously is defined by the probability of A and B both occurring divided by the probability of B, the conditional part. I told you before that in conditional probability we have some prior information. We are aware of B, and by considering this prior information we are going to obtain the probability of B. In fact, we are going to update the probability of A, but sometimes this prior information has impact on the probability of A, but sometimes the prior information about B doesn't have any impact on A. In this case, we say that A and B are independent, and we are going to talk about this in details in this session. Now, what are independent and dependent events? For example, two independent events are two events that have nothing to do with each other, and two dependent events are events that one event determines the outcome of another. It means one of them has impact on another one, but here they don't have any impact on each other. Look at here, Sheldon killed by bees because his uncle was killed by bees. There are independent events. You remember that we talked about this example in conditional probability. Suppose the experiment is rolling a dice, so the sample space is 1, 2, 3, 4, 5, and 6, and the probability of observing 1 is 1 divided by 6. It's an unconditional setting. But what about conditional setting? If someone told us if someone tells us that an odd number has fallen, then what is the new sample space and what is the probability of 1? When we know that an odd number has fallen, So 2, 4 and 6 are impossible. So the updated sample space or the updated possible outcomes are 1, 3 and 5, and the probability of 1, given that an odd number has fallen, is 1 divided by 3. You can see that this information, this prior information, had impact on the probability of A, because now the probability of 1, because now the probability of 1 is more than before. But what if someone tell us that the outcome or the observed outcome is a number less than 7? What is the updated sample space? Okay, all of these outcomes are again possible, because all of them 1, 2, 3, 4, 5, 6 are less than 7. So again the probability of 1 is 1 divided by 6. So this prior information doesn't have any impact on the probability of 1. So these two events, the events of observing 1 and observing a number less than 7, are independent. Look at this definition. Two events A and B are independent if the probability of A given that B is equal to probability of A and are dependent otherwise. So the probability of 1 given that observed outcome is less than 7 is equal to probability of 1. So these two outcomes are independent. So according to the definition of two independent outcomes, two outcomes are independent if the probability of A given that B has occurred before is equal to probability of A. It means B doesn't have any impact on A. And also, which implies that the probability of B given that A has happened before is equal to probability of B. So if A doesn't have any impact on B, it means B also doesn't have any impact on A. So you can see again here the probability of A given that B is equal to probability of A. So new condition provides no new information. So this condition doesn't have any new information for us, because we already know that all the outcomes are less than 7. Now we want to show that if the probability of A given that B is equal to probability of A, then the probability of B given that A is equal to probability of B. So one of them is assumption and another one we should prove it. So we assume that the probability of A given that B is the probability of A. Now we want to prove that probability of B given that A is equal to probability of B. So we start from this part, the probability of B, given that A is the probability of A intersection B divided by probability of A. Again, according to the multiplication rule, we can write it's the probability of B, probability of A, given that B, probability of A. So based on this, we know that the probability of A given that B is probability of A. So we showed that the probability of B given A is the probability of B. So if asked to show that events A and B are independent, or if we want to check if they are independent, we should show or verify that the probability of A given that B is equal to probability of A, or the probability of B given that A is equal to probability of B, one of them. You can say or, one of them is enough. Now look at this example. A card is chosen at random from a standard deck of 52 playing cards. Without replacing the first card, a second card is chosen. The probability of the jack on the second pick, given that queen was on the first pick. So because quiz was on the first pick and the sampling is without replacing, so the number of cards in the deck is 41, and because the first one was a queen, not a jack, so we still have 4 jacks in the deck. So the probability of jack, given that the first one was queen, is 4 divided by 51. But now look at this one. A card is chosen at random from a standard deck of 52 playing cards. After replacing it, a second card is chosen. Now, what is the probability of jack on the second, given that queen was on the first pick? So now it's the sampling with replacement. So after choosing or after picking a queen, we put it back, and so we still have 52 cards in the deck and with 4 jacks. So the probability of jacks on the second pick, given that queen was in the first pick, is 4 divided by 52. So you know that the probability of jack, the unconditional probability of jack, is 4 divided by 52, because we have 52 cards in total, 4 of them are jacks. And you can see that here the probability of second jack, given that this prior information is the same as the probability of jack. So this, in sampling with replacement, these two events are independent, but in sampling without replacement, these two events are not independent, because the probability, the conditional probability, is not the same as the unconditional probability. So this event, the queen on the first event, has an impact on this event, the jack on the second pick. Now this example, James is interested in the weather conditions and whether the train he sometimes takes runs on time. For a year, James records whether each day is sunny, cloudy, rainy, or snowy, as well as whether the train arrives on time or is delayed. The results are displayed in the table below. Is the probability of the train being delayed depend on whether or not it is a snowy weather? So we want to see that if a snowy is independent from the delay in the arriving time of train or not. So we are going to calculate these two probabilities, for example, probabilities of A and the probabilities of A given that B. We can show these two events with D, delay, and S for snow. So we should show that the probability of delay given that snow is equal to probability of D or not. So the probability of delay. You can see in a year, it means in 365 days, only in 35 days train had delays, so the probability is 35 divided by 365. But what is the probability of D given that S is the probability of D and S and probability of S? So the probability of S at first, snowy. In 365 days, only 20 days were snowy. So the probability is 20 divided by 365. And the probability of delay and snow, delay and snow, it's here 12. Delay and snow, in 12 days the weather were snowy and the train had delay. So the result is 12, 20. You can see that these are not equal. So D and S are not independent. It means they are dependent. Now look at this proposition. A and B are independent if and only if the probability of A intersection B is the probability of A times probability of B. So you see, if A and you saw that if A and B are independent, so the probability of A intersection B is the probability of A. So we can rewrite the multiplication rules for independent events, two independent events like this, because before we had in multiplication rules, before we had the probability of A intersection B is the probability of B given that A. So when A and B are independent, so the probability of B given that A is the probability of B. So we can write the probability of A intersection B is the probability of A times probability of B. So if asked to show the events A and B are independent, you can also show these equations, or you can verify this equation as well as these two equations. It's the proof that I showed you before. Now look at here. If A and B are independent, then the probability of A intersection B is the probability of A multiplied by probability of B. But if A and B are independent events, then A prime and B are independent. A and B prime are independent, and A prime and B prime are independent. So the probability of A prime intersection B is the probability of A prime times probability B. The probability of A intersection B prime is the probability of A times probability of B prime, and the probability of A prime intersection B prime is the probability of A prime multiplied by probability of B prime. So please memorize this equation because we need this equation in exercises. So remember that if A and B are independent, then A prime and B are independent. A and B prime are independent, and A prime and B prime are independent as well. You can prove this equation easily. Now look at this example. Consider randomly selecting a student at a certain university, and let A denote the event that the selected individual has a Visa credit card, and B is the events that the individual has a MasterCard, and the probability of A is 0.5, the probability of B is 0.4, and the probability of having both of them, it means a MasterCard and a Visa card, is 0.25. Are A and B independent? So we can use this equation to show the independency, or this one, but one of them are enough. So in this example we are going to use all of them, but I told you one is enough. So the probability of A given that B is the probability of A intersection B divided by probability of B. The probability of intersection is 0 to 25 and the B is 0.4, so the result is 0.625. You can see is not equal to probability of A, so A and B are not independent. But if we want to use this equation again, the probability of B given A is the probability of A and B divided by probability A, again 0.25 divided by 0.5, and the result is 0.5. You can see that the probability of B is 0.4. Again, the probability of B given A is not equal to probability of B, the same result. Or if we want to use this equation, the probability of intersection is 0.25. The probability of A times probability of B is 0.2. Again, you can see they are not equal, so A and B are not independent. But what is the difference between independent events and mutually exclusive events? A and B are mutually exclusive if the probability of intersection is 0. But A and B are independent if the probability of intersection is probability of A multiplied by probability of B. It doesn't mean that the probability of A and B is 0. In mutually exclusive events, A and B doesn't have any outcomes in common. They are completely disjoint. A intersection B is empty, but in independent events A and B have outcomes in common. The intersection is not empty. So look at this example. In experiments of rolling a dice, A is the even numbers, B is the odd numbers. They are mutually exclusive, so the A intersection B is empty or null, and the probability of empty events according to the proposition 1 is 0. But you can see that the probability of A times probability of B is 3 divided by 6, or 1 divided by 2, times 1 divided by 2 is 1 divided by 4. And it's not 0, so the probability of A intersection B is not equal to probability of A times probability of B, so A and B are not independent. So A and B are mutually exclusive, but A and B are not independent. It is impossible for mutually exclusive events to be independent. because the product of probability of A and B should be 0. And if both probability of A and probability of B are positive, so it's impossible. Independence for more than two events. For two events, we discussed that A and B are independent if and only if the probability of A intersection B is the probability of A times probability of B, or the probability of A and B both occurring is equal to product of probability A and probability B. But what is the definition of independency for more than two events? For more than two events, look at this definition. Events are more than two events are mutually independent if the probability of the intersection of any subset of them is equal to the product of the individual probabilities. So if you have any subsets of A1 to AN, it means subsets of 2 of them, or 3 of them, or 10 of them. So for all of these subsets, you should show that the probability of the intersection is equal to the product of the individual probabilities. This must hold for every single grouping of AI. So look at here for three events. For three events, for any subset, what's the meaning of any subset? When we have, for example, A1, A2, and A3. At first, groups of 2, and then groups of 3. So with combination we can obtain that we have 3, the number of groups with 2 elements from 3 events is 3, and groups of 3, it's choosing 3 from 3 is 1. So we need to prove 4 equations. But which equations? 1. A1, we start from groups of 2 events. A1 and A2 should be independent. A1 and A3 should be independent. A2 and A3 should be independent, and finally 3 of them should be independent. It means we should show that the A1 intersection A2 intersection A3 is the probability of A1, probability of A2, and probability of A3. So you can see we have 4 equations that we should verify them to prove that A1, A2, and A3 are mutually independent. For example, if these 3 equations are valid, we will say that the events are pairwise independent, but uh, but if all of them are valid, we will say they are mutually independent. So with this three equation, we can say they are pairwise independent.